Yeah, well, thanks for accepting my talk, and happy to be here. Yeah, so I'll jump right into it. So I just have some few disclaimers. So essentially, I'm not a RCPP expert, so hopefully many of you relate. So it was really my first jump into it and try. Okay, I've heard so much, wonderful things about it. I want to give it a try. I'm not going to talk like in general. So maybe the title, after I submitted, I realized that the title was a bit like, oh, maybe this is too broad. So I'm really talking about one specific, case, user case. I'm essentially porting a genetic algorithm from pure R into C RCPP. So excuse me if the talk was a bit misleading, but anyway, so I'll take that. And lastly, this was essentially an undergrad summer project. One of those summer projects that took about a year to finish, and Jordan here was great, and he did most of the work, to be honest, so I cannot take that credit. I mean, I did the benchmarking, making sure that things worked and what I expected and whatnot, but really Jordan is a student here at U of T. He graduated last year, or this year, I should say. He's now doing interesting stuff at Walmart, interesting enough. So, okay. So, I mean, the goal, as I already said, so essentially convert this genetic algorithm that from a pure R implementation into C++, so leveraging on RCPP, basically RCP Armadillo. Probably I may not need to say, so I'm probably gonna go fast through this, but what's RCPP? So, I mean, it's allows to integrate very easily R code into, C code into R. So you can, it's very flexible, creates all of these constructors and things that I barely understand, but allowed to do things very quickly and very easily. So that's really cool. So, I mean, Dirk here presented earlier. So he essentially takes the job of maintaining RCPP among probably other, dozens of codes. And I don't even know how he handles maintaining all that sort of software, but it's great. Thanks for all the work. Yeah, so essentially this has enabled further implementation. So I'm most of the work really rely on RCPP Armadillo, but there are other very cool work relying heavily on RCPP. As this count that I made, like over 2,800 reverse dependencies. So you can imagine, right? I know the last count of a CRAN available package, but I think it's about 10,000 or so. So maybe this is quite a bit of the packages is really depend on RCPP under the hood. So which talks about the relevance, right, of RCPP these days. So just going to talk about the motivating problem very briefly. So I'm talking about like two-phase studies here. The idea, I work mostly in statistical genetics. So the idea here is, say, some of you may or may not be familiar with GWAS, but the idea is running these large-scale genome-wide association studies, try to identify mutations in the gene that may be associated with certain traits of interest. And that's typically done in what I'm calling here a phase 1. And this is typically a large N here. And maybe if you're lucky, you maybe identify a region or regions in the genome that are associated. But GWAS only tells you kind of part of the story. It only tells you, okay, which location, but not really what mutations they really are really causal ones. So for that purpose, you really want to do sequencing, or next generation sequencing would be one thing to do, or what is called sometimes as fine mapping. But that could still be a little bit expensive, so you may not have enough money to do it on everyone. So you want to identify maybe a subset of people here that a subset of people in the phase 1 that provide more informative information. You would use something like the trait and maybe covariate information, maybe your GWAS hits or something along those lines to inform this phase 2 sample and the small sample size here. Small n over here, and that's become important. Essentially, the challenge really becomes how to select these most informative small n people. That's essentially the motivating problem here. Okay, so okay, why? So again, some of you may or may not have heard of genetic algorithms before. What it is and why using it is essentially a stochastic optimization method that will rely on nature's evolution, so ideas of survival of the fittest kind of thing, like use genetic information. I'm going to talk about what I mean by genetic information in this particular case, essentially using an initial population, and it sort of evolves it over time, and assuming there's some objective functions, some fitness criteria, let's say, it will over time based on certain operators like mutations and so on. And this will hopefully be clearer for in the next slide, but the idea is to identify kind of like the fittest members at the end, and that will be kind of your optimum. Okay, so why is genetic algorithms nice? Because they are suitable for discrete optimization, which is this is the kind of problem that they typically excel at in larger spaces. In this case, 2 to the capital N over here, roughly. And another nice thing is that it accounts for this budget constraint, which in this case, N, assuming that you have like a big fixed budget, you need to account for that potential a subset as that budget constraint. So, I mean, this is sort of the proposed genetic algorithm. So we start here on the left on the population, started with initial population. So essentially these R vectors over here is a vectors of zeros and ones. And essentially all the sum across columns here will be equal to small n. And we provide a initialization of those and random initial populations. So for each member of these populations, you calculate some fitness function, which in this case, it has to do with, in this case, it's not really important over the software perspective, but in this case will be something along the lines with the Fisher information matrix, that we want to have nice properties of that Fisher information matrix. And then you essentially loop over a bunch of different, say, generations, it's called in a genetic algorithm. It will iterate for a fixed number of times here. And, every time that, as long as this, it hasn't finished all the number of generations that you initialize in advance, it will perform different, the operators that I mentioned before, like selection, crossover, mutation. So it will try to take elements from here, take information from both of them, and I introduce some random mutation, and that's where the stochasticity of this method really comes into play. And then, based on, after selecting this, it will essentially generate like a new population. And for this new population, you again compute the fitness for each of the members and so on. And then you start iterating as a fixed amount of times. And then eventually at some point, it will reach a sort of like an optimum, this R star that I'm calling over here. Okay, so hopefully that was relatively clear what the genetic algorithm in this case is doing. So, I mean, the space here that you're really optimizing is over these kind of vectors, which are, of course, discrete. And yeah, so finding the typical methods don't necessarily work because you need to find usually derivatives and things like that. And in discrete spaces, that's complicated. You need to think about differences and so on. So, okay. In terms of the R implementation, we use actually, there was an existing package, thankfully, that checked many of the boxes that we were looking for in terms of the kind of optimization that we were interested in. In particular, this paper here by Mark Waters on the genetic algorithm. And yeah, it was a fairly neat and simple function, very flexible. So you see here, I mean, I didn't put obviously all the code, but really the user only needs to provide 3 parameters. So your n, k, or the objective function. And the objective function is to be defined in pure R. And again, this n in the example will be what I mean, a capital N, and k here will be the small n. I mean, there's a bit of disconnect there with the parameters. And then the rest of the things are just kind of hyper parameters or tuning parameters that you need to make sure that, according to the problem at hand, make sure that they perform as they do. But yeah, other than that, it's pretty neat. So it performs some for the crossover and whatnot. I think they use some tournament strategies, and it was a pretty nice code. Yeah, again, suit perfectly for our purposes. So yeah, so that's the R implementation. So we essentially wanted to port this function as best as we could to RCPP. So you can have a look at the implementation or the implementation that Jordan did in this GitHub page. And so we face a few challenges in the beginning. So as I said, we use our Armadillo to a lot of the objective function perform a lot of linear algebra operations. So that's the reason why we use our CPP Armadillo for that. So at some point you need to convert R matrices to Armadillo, but that seemed to be slow in the beginning. So essentially, we again looking at Stack Overflow posts and whatnot. We were able to figure out, so we had to do with some pointer, the way to convert the matrices using pointers. That was really the way to go. And then other challenge was, in some cases, there's no always equivalence from R functions to RCP, so one needs to code them, themselves. So for example, something as simple as the rank function with this particular ties method handling was not as easy to perform. So actually, Jordan spent quite a bit of time in again, Stack Overflow and whatnot, asking for help, and yeah, we were able to solve this in any case. So at least a fair approximation of what the rank function does in R. And I call it basic because even though we may use it all the time in R, doesn't mean that the underlying code is simple, right? So anyway, so that's what I said there. Yeah, and so maybe one of the biggest things here is that now, before we gave us a bit of flexibility, right? So the initial function have this flexibility to provide the objective function in pure R. So essentially, the user could provide anything, right? So we have to give up that sort of flexibility in terms of just putting, really customize it to our problem, right, at hand, which was using that lambda function that I showed you before. That had to do again with deficient information metrics and whatnot. But then we had to code that into C++, and we actually at some point, things that are very intuitive and very easily handled in R, like different cases, for example, had to evolve into 4 different functions in C++. So that part was kind of like again, there may be a more efficient way of doing things, but yeah, so that's how we solve it. Yeah, then lastly, I really wanted to benchmark, see, okay, what's really is there any gain here? Right? Is it really worth all this effort, right? And yeah, basically the performance, so making sure that they are providing the same thing, or at least a similar thing, and the timing, right? Which is the most important part. Of course, we evaluate different scenarios, simulate the different data sets, and perform multiple checkings. Essentially, we check all these different sort of values, but I'm focusing mostly on the sample size, the number of generations, and the initial populations, which may be more relevant. And of course, I have different optimality criteria, the objective functions, but I'm gonna focus on the other 3. Okay, so in terms of performance, so I'm focusing only on when the number of generations is equal to 1,000. So here on the y-axis is the standardized objective function, because I have different initial data sets. The initial populations are always the same, but because one runs in R and the other one runs in RCPP, the random number generators and whatnot are different. So they're not exactly, they won't match necessarily 100%, but as you can see, they are close enough. There are 2 lines in there, one purple and one gray, and the bands are sort of the different sort of the errors, so the range of the different values that it reached. So the horizontal panels are the number of the initial population size, and the horizontal ones are the sampling fractions that effectively translate to the phase 2 sample sizes. And overall, this is kind of what you want to observe. You want to observe that at some point the genetic algorithm sort of plateaus, meaning that it reached already a sort of a stable-ish solution. And overall, I mean, you see that, again, both implementations reach similar results or similar stability over time, which is what you would like to see. And yeah, and then again, maybe what people may be more interested is in the timing. So here I'm just plotting the time in minutes here. And maybe going back a little bit, I mean, the reason why I really want to do this is because the R implementation was slow, which is one of the things that people usually complain about these genetic algorithms. They are typically slow. They take some number of generations to run and so on. So it's like, okay, I really want to squeeze some of that timing by using RCPP or Rcpp Armadillo as well. And yeah, so you can see here, similar as before. So here are depending on the initial population size, so the number of R, if you will, that they're started, and the sample size. So you see some gains. The gains are not super uniform throughout. I mean, here I'm gonna switch in a second to log of the time to make those differences more noticeable. But I mean, there's some gains overall. So the RCPP implementation is in gray here, but I mean, not super consistent across the board. So anyway, so here I'm taking the log across things. Yeah. So yeah, overall there's some gains, but again, you know, they are more noticeable, or at least tend to be more noticeable as the number of generations increase, as you would expect. Yeah, I guess just to finalize here. So yeah, I mean, we had to do some trade-offs here. So the implementation that we put together was lack the flexibility on the objective function, but you know, that's kind of the how we could solve it. You know, you probably all know, but Stack Overflow is a friend, so there's lots of, you know, the community is really nice. Dirk is, you know, he's very, you know, active in that. So I'm also surprised that he even has time to answer questions over there. So that's amazing. So yeah, I mean, there were some time gains, which is great. Maybe not as striking as we, you know, in other problems, you'll see, you know, huge increases in the time. This is not that surprising because, you know, in the genetic algorithms, the new generation depends on the previous one, kind of like MCMC kind of problems where it's known that there are some gains, but again, not as striking. There may be some other squeeze in improvements that I could gain in time, maybe part of the evaluation of the objective function, because I'm using linear algebra, maybe some of these tricks can be improved. And, you know, but really bottom line is there's no free lunch, right? You know, there's always need to keep some things, and there's some trade-offs and so on. So hopefully I didn't go too much over. Thanks for your time, and happy to take any question. Yeah.